Okay, here is our list of LaPlace transforms of various functions. We have going down to the sine of kx, and then just beneath that cosine of kx. And again, to remind you how similar these are to their hyperbolic functions, where for the hyperbolic sine of kx, it is k divided by s squared minus k squared, and for the sine, of course, it's k over s squared plus k squared. And the hyperbolic cosine is s over s squared minus k squared, where for its cosine counterpart, that would be s over s squared plus k squared. And in one of the recent videos, we determined that if you have a constant raised to a variable power, its corresponding LaPlace transform is 1 over s minus k times the natural log of that constant. So that's the table of transforms to date. What we're going to do in this video is determine another property of LaPlace transforms that will enable us to expand our table here. And of course, you want to point out that all the LaPlace transforms that we've derived, every one of them are some function of s. And the reason for that, of course, is the way that the whole definition is set up, like ab initio. So let's just talk about that for a second, because that is going to lead us into something a little bit different. So we know that the integral of f of x e to the minus sx dx, where x goes from 0 to infinity, we're integrating with respect to x. And then once we integrate that, then we're going to get a function that has x terms in it, and it will also have that s term in it. Then the x's that are there, we substitute 0 and infinity for those x's. So the x variables go away. They have specific numbers substituted for them. The only trick was that we had to stipulate s, so if we put infinity in here, we would not get an improper integral. But we went ahead and carried on this process then, we ended up with some function f of s. For example, the very first LaPlace transform that we determined was when f of x was just a constant. So then we had a constant times this integral e to the minus sx dx, and that equals e to the minus s times x. And out here we had minus c over s, and s goes from 0, or x goes from 0 to infinity. And then we had to be on the lookout that that part of the exponential, that is always positive, so that when you put infinity in here, you're going to have e to the negative infinity, which is 0. And it's better to have 0 than have the whole thing just blow up. X is always positive because x goes from 0 to infinity. So that means then that s, likewise, has to be greater than 0. And then with those constraints, we get minus c over s, e to the minus infinity, or 1 over e to the infinity, minus x is 0, we have e to the 0, which is 1. So this gives us plus c over s. Now suppose we had this kind of an integral. We had, it could be multiplied by c, that's fine. And we have e to the minus s minus k times x dx, where k is just another constant. And this will be equal to minus c over s minus k times e to the minus s minus k x, where x goes from 0 to infinity. So if this part here is negative, then we want to make certain that this part in here is positive, so that we have e to a negative power. So we put infinity, we're getting e to the negative infinity. So we want to ensure that s is greater than k, and with that stipulation, this equals, let's write it down here, this equals minus c over s minus k times e to the negative infinity, 1 over e to the infinity, minus e to the 0, which is 1, and this will equal plus c over s minus k. Our point is that if instead of having just minus s of x, you have minus s minus k, then you don't get a function of f of s. Instead, you get a function of f of s minus k. So that, in general, we can say the integral from 0 to infinity of f of x e to the minus s minus k times x dx. That integral there is going to be some function of s minus k. And before we try to look at the significance of this, let's multiply this exponential out. This would be e to the minus sx times e to the plus kx. So you have it like this. Times e to the minus sx dx, and that in general equals some function of s minus k. So what that means then is, if we have some function f of x, and its corresponding Laplace transform is just some function f of s, well, suppose we take then this exponential function, e to the kx, and multiply this function by that. Now, what will the Laplace transform be for this function? We have our original function multiplied by this exponential. Well, it's right here. This is the Laplace transform of e to the kx f of x, and that equals some function f of s minus k. So, if our function f of x has a corresponding Laplace transform function of f of s, if I multiply that function by e to the kx, then the new Laplace transform is going to be the original one, only now we have s minus that k term. So, let's think of it like this to get the most value out of these relationships. Here, we're saying that looking at it from this side and going over to this side, we're saying, well, the inverse Laplace transform of f of s, that's our function f of x. Looking at this side and going on to that side. Likewise, we can say, well, then the inverse Laplace transform of f of s minus some constant, that will equal our original function, f of x, times e to the kx. Here, this is f of s. This is the inverse Laplace transform of f of s. That's what f of x is. So here, the inverse Laplace transform of f of s minus k, that's our original function f of x, multiplied by e to the plus kx. Now, one more change we can make. What is f of x? It's this. So we can replace that with this. And this, we're making a big deal out of this because this is a very handy tool that we can use. We're going to use it in the next video. For example, suppose that we wanted to take the inverse Laplace transform of 15 divided by, say, s squared plus 4s plus 13. What does that equal? We have no way at this point of determining that inverse Laplace transform. But if we use this relationship, then we can solve it. And that's what we're going to do in the next video. Learn how we can use this relationship so that we can take Laplace transforms and all new types of functions that here before we were not able to handle. So come back, join us in the next video, and we'll make some practical value out of this relationship.